Okay. Yeah, Brian. Okay, you can go ahead. Okay, guys. So, welcome everyone. Today we're hosting Dr. Efrosini Charalambous. I'm gonna introduce her fast. I mean, I'm sure most of you have took a look at her work, but in all cases, she's a research fellow tutor at the UCL, the Faculty of the Built Environment. Her work resonates a lot with this series in terms of what it covers regarding behavioral neuroscience, spatial cognition, the architectural space, and much more. Her work rotates mainly around this, and then she was as well using spatial analysis technique as well as EEG analysis. So, I mean, as usual, the format is going to be, I mean, she's going to go ahead with her presentation, and then after that, we're going to have like an open discussion and some questions and answers. So, Efrosini, the floor is yours. And looking forward to your presentation.
Thank you for the nice introduction. Thank you everybody for coming here. I have some background noise. I hope it doesn't really make a lot of an issue. And also my camera, I know that it's here, but I'm looking at my biggest screen, so that's why. I think it's a common issue, so it's okay. I'm looking at you anyway. So I've finished architecture at the NTUA, the National Technical University of Athens, and then I did my master's degrees at Barcelona, in Barcelona at IAC, the Institute of Arquitectura Avanzada de Catalunya. And then I started working as an architect, but at the same time I was involved in dancing and in meditation, so I started getting interested in how the mind works. So I started my PhD at UCL, which I finally managed to finish 1 year ago. So the work I'm going to present is part of my PhD. And let me start sharing the screen.
Yeah, please.
Yes, it's this one. Sure. I think you can see it, right?
Yeah, we can see
it. Great. So yeah, the work I'm going to present here is part of my PhD research and has recently been published in Spatial Cognition and Computation under the title "Aha, I Know Where I Am." So for my PhD, I used, as Firas said, space syntax methods, which are spatial analysis techniques, and to examine the behavior and brain responses related to the specific experience of reorientation. So the main idea was that studying the spatial experience and brain dynamics in real world complex situations is really not a trivial thing. And that's why usually lab experiments, although they have the advantage of controlling for different variables that affect our behavior, and that we can study the different dynamics, neural dynamics. They do not necessarily represent how we relate with the built environment. Therefore, in order to be able to explore these questions in real-world experiments, we need to have some quantitative spatial descriptions. That means need to have tools to measure the spatial properties in an objective manner. And in this way, we can examine the experience of behavior and brain dynamics in relation to the specific contextual measures. For example, space syntax is for those who are not familiar, I'm just providing here a very brief introduction. It's a quantitative environmental modeling technique, and it was pioneered in the 70s by Professor Hillier and Professor Hansen and other colleagues at the Bartlett at University College of London, and provides a set of theories and methods for the analysis of spatial configurations, and a set of techniques where we can use to analyze spatial layouts and the human activity patterns in buildings, but also in urban areas. There are different tools which are usually used within the space syntax community. These are, for example, Excel map analysis, which involves the analysis of a connected graph of Excel lines to investigate urban systems. These lines are the locus lines of sight within the environment. There is a book and a lot of theory behind this and different kind of measures to support this. On the other hand, there is like the isovis analysis, which is the analysis of properties of the visible space from a given point in space. And the shape and size of an isovis changes with position. Another very useful tool is the one that I use, is visibility graph analysis, which connects mutually visible points in a graph data structure. That means it combines isovis analysis with axial graph analysis. And it creates a grid, a grid of cells within the environment, and then calculates the graph measurements of this grid in the isovis of these grids. So space syntax has been often and lately used also for the study of spatial cognition, and there are several studies that have focused on the relationship between space syntax and spatial behavior and cognition. Also, they study wayfinding, spatial memory, and they use different kind of different methods, such as map sketching, to access and evaluate the cognitive maps of different neighborhoods, pointing task, to examine spatial memory, think aloud protocols, or tracking of individuals to examine behavior. I just want here to present, there are a lot of studies, but I just want here to present a very recent study which shows that these spatial measurements of space syntax might actually have a correlation with activity in the brain, which is very interesting. So a recent study done by Javadi and colleagues in 2017, using brain image techniques, has shown that there is an association between activity at specific brain regions and the topological properties of the environment, that is graph-based measurements of the environment. So in this case, the researchers examined participants' brain activity using fMRI, while they navigated and filmed simulation of an area in London that they have recently learned. So participants has to indicate at certain street entries, such as here, for example, the direction of the shortest path to the goal. So brain activity during these events was analyzed in relation to the specific space syntax measurements that were able to capture these complex aspects of the environment, such as, for example, how many other streets at a given street is connected, how many other streets a given street is connected with, which is like the degree centrality. So they found that the posterior hippocampal activity correlated with the changes in degree centrality at these points. And they also found a correlation between the anterior hippocampus and another graph measurement, which is the measurement of closeness, which is reflects the highest closeness centrality values. In this case, reflect that how topologically close is the street to other streets. So we can see like different parts of the hippocampus, which is traditionally related to navigation, is sensitive to these different measures, which supports the working hypothesis that indeed we can use space syntax measurements to examine the brain response. So the work I'm going to present now is focused on the aha experience of reorientation. That is the sudden and spontaneous transition from the state of being disoriented and lost into a state of being situated in space and oriented. So we're talking about this sudden transition. And I think getting lost in cities is a feeling that we often experience. And we usually have this experience, especially when we exit the underground station. So our sense of direction is not anchored to the external overground world. So we walk towards one direction and then we suddenly realize that, oh, we are completely the wrong direction. So I wanted to pinpoint that experience and examine what happens. So this sudden feeling of presence, which can be described as a gut feeling of being in a specific spatial context and intuitively and spontaneously knowing where one is with respect to the immediate surroundings. So this to get a sense of the nature of this experience, imagine the mental impasses and distress we feel when our sense of direction is lost, and the quality of the experience that arises when we suddenly know where we are. So in this case, researchers suggest that there might be a change, a switch in the mental representation that is associated to this sudden transition in knowledge, in the knowledge state, in sudden knowledge acquisition, let's say. So my research question was, in what sort of spaces, what sort of places in this moment is more likely to occur within the built environment? So theories from environmental psychology pointed towards two spatial qualities which are psychologically relevant to exploratory behavior. So the hypotheses of the study were based on these spatial qualities. So we have the hypothesis spaciousness and the hypothesis complexity. So the quality of spaciousness relates to the amount of visual information. And within the environmental psychology theory, it relates to the sense of prospect and refuge. On the other hand, complexity, according to theories of environmental psychology, is related to the concepts of predictability and mystery, which are considered drivers of exploratory behavior. So one hypothesis is that the moment of reorientation will be related to a sudden change in the amount of visual information, which can be measured by the isovist area, change in the isovist area. And then the complexity hypothesis that the moment of reorientation is related to change in the complexity of the visual information. To capture the complexity of the visual information, I use isovist clustering coefficient, which captures changes in the complexity. So at low values, where locations with low values of clustering coefficient are locations with multidirectional fields of view, where a new area of the system may be discovered, which points towards the predictability and mystery quality, spatial quality. So the objective of the study was to investigate the interrelation between spatial properties and this aha experience of reorientation. So I used the isovist analysis and visibility graph analysis to quantify these spatial properties and to test the hypothesis and examine how these spatial qualities are related to the behavioral and neural responses. So the data analysis is based on spatial data, behavioral data, and EEG data, and their combination. To capture the neural responses, I recorded participants' brain activity while they navigated a virtual reality environment. So I used EEG, which is electroencephalography, which is a method of recording the electrical signal from the human skull, using specific EEG headsets, like the one that you can see in the image. So in this study, I used the Motive headset, which is, first of all, affordable, and a wireless EEG headset with 14 electrodes placed on the human skull. So usually neuroscience and neuroscientific studies are interested in different conditions, in the differences between different conditions within an experiment, because they may elicit different cognitive responses. So these responses are reflected by differences in the brain activity patterns. Therefore, we usually examine and process the EEG signal in relation to these different conditions. And so these were the virtual reality environment where participants were asked to explore three, let's say, city environments while they were wearing the EEG headset. So these city environments represent real urban regions, and they were created in Rhino. And the game environment was created and developed in the game engine Unity 3D. So these real urban regions are European cities, or let's say part of European cities, which I've tried to alter a bit or maybe mirror just to prevent any issues of familiarity people have lived in some of these cities. So the first one is a neighborhood in Athens. The second is in Barcelona, and the third is in London. So 20 participants took part in the study, 9 female, and their mean age was 33 years old. So there were not like any age-related differences between participants because they were all relatively young. And each participant had to take 8 trials in each of the 3 environments. So in total, I was able to collect 24 data from 24 trials from each participant. And these 3 environments, I compare them using the measure of intelligibility, which is again a space syntax measure, which shows the degree to which a certain environment is legible, and therefore the ease to which one can navigate within the environment. And their degree, let's say their ratio, was similar to all 3 environments. So therefore, I was able to aggregate these trials as a set of trials and examine together. So to describe formally the 2 hypotheses, as I've said, of environmental change, I use the visibility graph analysis, which results in these representations of the built environment. The first row, it shows the isobist clustering coefficient, and the second, the isobist area. So the colors from blue to red represent the range of values of the isobist properties of interest in each case. Let's see. So this is the experimental procedure that participants followed. So before each block of trials, which was the set of 8 trials in each virtual city, let's say, participants studied the map of the urban environment. After they were ready to proceed, they press the ready button, and then they begin the trial from a random point of origin. They were asked to explore the 3D environment and press a button when they had the feeling of knowing where they are. And then the response graphic user interface appeared on the screen. So participants pressed the key to give their response. The map appeared on the screen, and then their task was to rotate the map using the mouse to align it with their heading. This is the usual thing that we do when we have physical maps. We try to rotate them in order to say, okay, I'm here facing there, okay, I have to go that way. So they also have to give their confidence degree just to check whether this is just a random response or they are certain about their response, to double check their self-report. So then I managed to collect the data, and then it was a big thing of analyzing the data. The first part of the data analysis was based on the relationship between participants' wayfinding behavior and the isobist properties. It involved 2 directions or subparts, where I first studied the spatial properties at the response locations where participants gave the response. But I also studied the changes in the spatial properties just before the response. So within a window 3 seconds before the response. So this slide here shows the isobist properties at the response location. The first row just showed participants' exploratory behavior, and the different colors are the different trials of each participant, which from from the same starting points, which were random in the environment. So participants started exploring the environment without knowing their actual location or orientation. So they were in a kind of a state of disorientation in relation to the external environment. Their task was to respond when they have the feeling of knowing their current location in relation to the map, when they recognize their location, in relation to their surroundings and the map knowledge that they have. So I first looked if there's a specific trend in relation to the locations participants tend to stop to give their responses. The histograms here show represent the frequency distribution of participants' responses based on the isofix values at this location. So on the left is the histogram for the spaciousness hypothesis, and on the right for the complexity hypothesis. For the spaciousness, we can see that there is no clear trend in the data, in the distribution. However, in the complexity, in the case of complexity, we see that the majority of the responses concentrates within the low range of values of clustering coefficients, which gives an indication that this might be a stronger hypothesis. So during their exploration within the environments, participants also search for spatial cues to understand where they are. So it was a particular interest to study the moments of environmental change just before participants' response. And the isofix analysis is the tool that offers it offers a good tool to measure these changes in the contextual information in relation to participants' path. So this can be done by unfolding the isofix values of interest along each path. For example, this image shows the area and clustering coefficient and how the isofix values in each case and for each trial, that is for each participant path, unfold within different time windows of 3 seconds. In this way, we can see changes in the isofix value and whether they are associated with participants' behavior, decision to respond. So what I did, I divided this period preceding the response into 3 time windows of the same length in order to compare the isofix values, the peak within these windows of the isofix values. So this results in these raindrop graphs, where they represent all the data points of each 20 participants, the mean, and the mean isofix value of each of the group of trials for each participant. So we can see that in the first case, I'm interested if there is a difference between the different time windows, but I'm more interested in the last time window, which preceded the response, because that shows that there might be an association. So I was looking to see if there are differences between the 3 seconds to 0 seconds in relation to the previous time windows. So in the case of isofix area, that is the spaciousness hypothesis, we can see that the statistical test found no significant differences. However, in the case of complexity and clustering coefficient, the mean value of clustering coefficient within the last time window is significantly lower than the previous one. The peak, the negative peaks of the clustering coefficient. So the minimum clustering coefficient is significantly lower. So this shows an indication of points, let's say, towards the complexity hypothesis, the behavioral results. So the next step was to examine the brain dynamics in relation to space. Again, the analysis has 2 main parts. So I used the EEG data to investigate the isofix properties at the response location. So the brain dynamics as an effect of the spatial properties at the response location. And then I used changes in isofix properties just before the response to investigate changes in the EEG powers. That is, I investigated brain dynamics as an effect of the changes in the spatial properties just before the response, within the time window of interest of 3 seconds just before the response. So the data for the brain dynamics, as I said, was collected using the embodied EEG headset. And I processed the EEG signal to examine the frequency of the signal at specific areas of the brain and specific frequency bands. So my main focus was based on relevant findings from the literature. And I focused on the theta wave, theta frequency, that is between 4 and 7 hertz, and alpha frequency, that is between 8 and 10 hertz. So I first look at the changes in brain dynamics that were associated to changes in the isovis properties. So in the image, you can see in the white, I don't know if you can see my cursors, when there is a peak change in the values. So my focus was there. So when there is a big rise in the isovis values of area, and a big drop in the isovis values of clustering coefficient, because this was what my hypothesis point to. So for this situation, I focus on the frontal channels. So this is the two frontal central channels, but also the frontal channels. Sorry, I forgot to put there a circle as well, and the EEG theta power in this case. So my question was, is there a difference in EEG theta power between two groups of small and large isovis changes? So what I did is I collected, I examined the EEG signal in relation to these peak changes, the moment that there was a peak change in the isovis value. Then I classified these changes into small changes and large environmental changes. And then I compare these two groups in order to see if there are differences in the EEG theta power, the frontal EEG theta power, which according to the literature is related to movement and sensory processing of environmental information. So what we can see here that's both area and clustering coefficient, that it changes, both changes in area and changes in clustering coefficient, seem to be associated with differences in EEG theta power. So the larger the change is in the area, the larger the EEG power is, and the larger the drop is, the drop of the values in the clustering coefficient, that is the lowest values in the clustering coefficient, they have the biggest EEG theta power. And these are significantly different between small changes and large isovis changes. And that is for all, averaging the EEG power over all 4 frontal channels, or just looking at left channels. But when we're looking just the right channels, we can see there is significant difference only for the case of clustering coefficient, but not for area. And usually the right side, the right hemisphere, is more closely associated with allocentric and place recognition, I think, rather than root processing. Place processing rather than root processing. I cannot remember now the reference of this paper. But anyway, what this shows is that although both measures and both properties, both qualities may be associated with a specific moment, their contribution might be different. Then the next part and last part of the analysis was based on the expected brain dynamics and how they are associated to each of its properties at response location. That is, my aim here was to compare the isovis properties between two groups, two cases, let's say. No? So the first group on the left, expected response, includes trials that exhibited the expected brain dynamics, which reflects cases where participants actually were able to suddenly understand where they are in the environment. And that's the reason they press the response button. So the specific pattern of brain dynamics that was expected was in accordance with previous relevant research. So more specifically, one component of the expected brain dynamics was alpha power degrees. So I have it here as alpha ERD, which means event-related desynchronization. It's a more convenient way than writing decrease in alpha EEG power. But that was the expected response as opposed to an increase in alpha EEG power. So this alpha power decrease was associated, according to again a recent study by Javadi and colleagues, with backtracking the behavior. That is, when you suddenly change the direction of your movement in order to minimize the path, the length of the path to the goal. And I think that's kind of the behavior that we do when we exit the tube and we go towards the one direction. And then we're like, oh, no, that's not a good idea. We will need to change our direction. So that's the backtracking behavior. And also the alpha response was associated with the integration of egocentric information into an allocentric reference frame. And this switch between reference frame is an important mental event associated often with the aha moment, even in insightful problem solving. So such an aha effect was expected during a spatial reorientation, since it's a moment of a transition from a state of knowing, of not knowing, to a state of knowing, a sudden transition, a spontaneous transition. And it's most likely supported by a switch in the mental representation of the external environment. Therefore, I classified trials based on the expected brain dynamics to enable the study, which enables me to study how isovis properties differ between the two cases. So, again, I focus here on the posterior alpha EEG power based on the literature. And my question here was like, is there a difference in the isovis value between the two cases? So I looked at the alpha power, I look at the clustering coefficient values between the two cases of alpha decrease and alpha increase. And I looked at the isovis area value between the two cases of alpha power decrease and alpha power increase. So we can see in the slide, I've circled the ones that are of interest. We can see that when we look whether there is a decrease at both parietal channels, the P7 and P8, or an increase, we can see that there is only, that's on the right hand side, the graphs, we can see there's only significant difference in the case of clustering coefficient. That is, again, the values are lower for the expected brain dynamics for the case of interest. When there is an alpha power decrease, the group of trials that showed an alpha power decrease the response happened at locations with significantly lower clustering coefficient values. And that's also the case if we just look at the right channel, the right hemisphere. However, in the change of isovis area, there are no significant differences between the two groups of trials, which again points towards the complexity hypothesis So that's this aha moment of knowing where one is suddenly is rather more closely related to a change in the complexity of the visual information. However, we cannot exclude that a change in the area contributes somehow to this experience, which of course, yeah, needs a bit more experimenting to understand how it is. So I hope I have managed here to show how a change in the environment is coupled with a change in the behavior and a change in brain dynamics. And thank you very much for your attention. I hope I managed to
Thank you very much.
Should I stop sharing my screen?
Right. That was like the trinity you tried to show was quite clear. Yeah, if you want.
Okay, great.
I mean, yeah, I see you have your email here if somebody wants to get in touch as well.
Exactly. And the paper, if someone wants to read a bit more about this, it's on spatial.
Yeah, actually, I went through it. It's like with the link you shared, it's online as well.
Okay, I'll stop sharing now.
Yeah. So yeah, like before we just move on, like for everybody, I mean, this is just a casual meeting here. So if anybody wants to ask any question or wants to join the discussion, just feel free to just unmute yourself and jump in. I have like I will start with because I have a lot of like, things and comments and things I think we can discuss for talking about with everybody here. So the first thing that I noticed is that you in your models that you were examining, you were taking into consideration mainly the isomist, which is like how much things you can see. But then, did you on purpose cancel all the other aspects? Because, for example, you stick to the formal aspect or the volumetric aspect of the city or the urban fabric, but then usually, I mean, I was wondering that, for example, there's a lot of things that in a city would keep you oriented, such as like signage, nature, activity of people, like the density of people walking. So, for example, in a lot of cities, you might get some orientation just by seeing how many people are gathered in one place or not, the presence of public spaces, and so on. So I want to know if like these parameters, I mean, you on purpose, you put them aside to stick more to how much we see and then just the formal aspect of it.
Yeah, well, that was exactly the problem with working in complex environments that I've talked to just before. Second slide, I think, of my presentation, which is in order to control all those different variables, because of course every little thing of information is a source of information, is a cue, and it's a cue in space, so it's a spatial cue. Even it's like a group of people or like a smell or like. So in order to control and to examine just one hypothesis, I tried to eliminate any other, let's say, variable. So in the 3D environment, there is no information. All the buildings are gray, just from random noises of some buildings that appear with a bit of texture, just to add noise and to make the experiment a bit more valid. And also, there is no visible sun. There are no clouds in the sky. There are no landmarks that one can see, from far away. Just in order to reduce the complexity in a way that permits me to control the situation. So if I see a change, an association between a difference in space and a difference in brain activity, my interpretation will be more or less valid, let's say, or logical. So otherwise, there are so many variables in the complexity of the world that we live that you cannot really capture it in an objective manner. In a subjective manner, that's a different kind of qualitative research.
Yeah, right. No, definitely. The thing, because I worked as well in part of my research with the same headset that you were using, by the way. And then like now I'm just thinking out loud that for example, like usually I mean, every time I'm in a new place, for example, I just ask like, where's the sea or where's the south, right? Or where's the north, just to orient ourselves. And then I'd like to know because in the cities you were talking about, like the whole idea of I think scale and then mass to void ratio plays a big role, right?
Sorry, can you repeat?
Yeah, like I'm wondering how like these two things can affect like the scale of the, I mean, whether it's like more human scale or less human scale, so the size of the buildings are related to the place that we are in. And then the other thing is the like the relation between mass and void, because in a lot of cities you have like a huge square with then a lot of urban fabric, and then some of them have like smaller size open space, but then a lot of it.
Yeah. I think first, I think that, and all these, I think, are aspects that are kind of missing from the research or the mindset of usual ways of doing research on spatial cognition and behavioral neuroscience. And I think, for example, the fact that I mean, the way that you read a map or the way that you acquire spatial knowledge is also related to the culture. So, for example, because I'm from Cyprus and I'm kind of used to live in cities with more organic grids, I really feel safe, let's say, or feel that I won't get lost the more maze-like is, or not, the more organic the grid is. For example, if all the streets lead to the central square of the village,
right,
or the sea, as you said. So I think we develop this knowledge based on the way that we live, on our history, on our culture, on all these different aspects, no? And on the other aspect that on the other point that you made about void and open spaces, and which also point to differences in grid, I think is also how we register events that are unexpected in space. Or, for example, because there is a frequency of, we register the frequency. So if we are in a big street, and the frequency of change is not that much. So if suddenly there is, I don't know, unexpectedly a big void, or a big park, then that's an event, a spatial event in our memory, in our maps, the cognitive map that we create. And all of these are related to the quality of the experience. And that's why I think that looking at the quality of the experience is a very important source of information. The difficult part is decomposing that and understanding what's going on. Yeah.
So then that could tie back to, because the experiments you were doing were in virtual reality, right?
Yes. Yes, I use the Unity 3D.
So how do you think that would differ? Yeah. So exactly. So I'm interested in two things here. So first of all, I mean, the obvious question, which is like, how do you think that would have differed if that was in a real environment? So if people were actually in a real environment, then that would actually, of course, get into the equation a lot of other parameters. And then the second thing that I'm really interested in is, because then the environment is internalized, so the environment is in the computer as well, so it's in software, and then what you're mapping is digital as well. So how can we? So I'm really interested in how we can actually change the design of the environment in Unity while mapping the brain activity or the brain mapping, and to improve the actual design, right? Because like now that you're collecting this data, and then you have this data set, let's call it, and then because the design and the actual design that was examined is in Unity. Unity, for the ones who don't know, is like I mean, just simplifies the modeling and simulation software usually used for games and stuff like that. So what I'm saying is that you can actually map a design at the same time in Unity, and then monitor how what you are designing could be received by a brain, right?
If I understand, I'm not sure if I understood correctly what you mean, but if I understood this, while, let's say, the person is navigating the environment, if changes can happen in the environment itself, or?
Yeah. Or could you cause that feeling of I don't know where I am by changing the map? Yeah, exactly. Yeah.
Okay.
So the thing is, okay, we have this urban environment, and then we assess it, and then get the brain maps, and then we do this on several ones, and then what we can do afterwards is not only to produce the aha moment, but then be able to control the environment to produce what we actually want as a brain activity.
Yeah. Of course, that was also one idea of
If
changing.
I explain this right?
Yeah.
Well, because
I
somebody
think,
is asking here in the chat. Yeah, could you cause that feeling of I don't know where I am by changing the map in real time? So you might be seeing that the person is responding well, and then you can actually change the map to get them in a different kind of thing.
Yeah.
To get them lost in a way.
I think, yeah, that could be. I mean, generally, it's the idea of teleportation that I followed. But of course, there is the other idea that the environment might suddenly change. What I wanted to do is do something that can happen in real life as well, in order to study the brain, rather than create an improbable scenario. However, this scenario, well, it's not so. Yeah, I mean, it can happen if one. So because I've also thought about this scenario of changing the environment, and that will be the case that you go to the bar, you get completely drunk, you have a blackout, and then you wake up in a completely different place. So that's what I'm interested in, just seeing if that kind of experience, the simulation of the experience, there is a relation between that simulation and real life. Because otherwise, I think that there is some kind of artificial there, and it's more close to lab and mice kind of experiment rather than an embodied.
Yeah, that could be really interesting here. Yeah, I mean, I think that's quite interesting because in your case, I mean, when you're internalizing the actual environment and the experience metrics, so let's say that you're quantifying the person and the environment in a digital environment at the same time. So I think this opens a lot of doors on how we can change the design of the environment while monitoring how that affects the brain. And we have other questions from the YouTube people who are watching on YouTube. So one person is asking about the cleaning process of the EEG, I guess, data. I noticed you had a few outliers. Do you remove outliers?
No, I didn't remove any outliers, but I followed the pre-processing steps, following my recipe book. I don't remember the author, sorry, but I coded all the processing steps I did were done in EEG lab, and then the frequency, the decomposition was done in MATLAB by following the recipe book and doing some modifications in the code to present that. But I didn't. I didn't.
Yeah, because.
I didn't remove the outliers.
To self-identify. People who are asking in the chat, you can definitely jump in. So I guess that's Jenny and someone else. Jenny, do you want to jump in, or should I ask her question? Okay, so I'll go ahead.
Okay.
She's asking, did you get participants to self-identify if they thought they had a good sense of direction? Yeah, I think that's what you were doing in the confidence metric, kind of.
Yeah, but I also
very confident, less confident, or very confident.
But I also use a self-report, the Santa Barbara sense of direction report, before at the beginning. At the end of the experiment, to see how people perceive their ability of or sense of direction, their sense of direction. And if I remember correctly, there was a correlation between the confidence ratings and their sense of direction score, if I remember correctly. I hope I answered your question.
Yeah. We have another question from Syed. Okay. I'm not sure I'm pronouncing it right.
Okay.
Do you want to having mic issue? Okay. So in research in including these states of unfamiliarity of the space, I am in by down regulating artificially with transcranial electrical stimulation on P7 and P8. So we can just say briefly what are P7 and P8 for people who are not familiar
P7
with
and P8 are the channels
1020 modeling. Yeah.
I'm not sure I understood. I'm trying to read again the question because I'm not sure I understood. This is inducing the state of unfamiliarity of the space, I mean, by downgrading artificially with transcranial. Okay, yeah. That's,
I'm not sure I got this right.
If there is in the literature any research based on that, I came across some transcranial, but I'm sorry, I cannot recall. I cannot recall. But if you want, just write me an email and try to look at my folders and see if I can find those. Sorry, bad memory.
I mean, from I've seen a lot of transcranial direct current stimulation and stuff like that, but none of them was related to unfamiliarity of space. So I think that would be quite interesting.
Mm-hmm.
Right. Oh yeah, I think they will email you. So okay, so like to jump like a bit. I mean a bit technically, but try to understand how that would translate to the real life. So you were saying you were using the theta and alpha frequencies, right?
Mm-hmm. Yes.
Okay, and then I'm sure several people are asking like how would that translate to actual real life? So what are alpha and theta waves tell us about like what we feel or the environment, or how does that relate? Like why did you choose these two specifically?
So I chose these specific areas. I isolated my analysis into these specific areas, let's say, because according to the literature, this kind of pattern were associated with cognitive processes that are related to the events that I wanted to study.
Mm-hmm.
So, for example, when you have an aha in problem solving, when you have an aha moment, according to the theory and also the experiments that they did, and there is a change in your representation, a switch in your representation. So suddenly you read a certain, I don't know, information using two reference frames. That's the theory in problem solving and the aha moment in problem solving. So when we have insights, let's say, so different kind of chapter. So I've studied that chapter and to understand what's happened in the brain when we have this like, aha, okay, I know now. And then in the spatial cognition and orientation, let's say, literature, it suggests that there is a similar use of two reference frames, and there is a switch during the moment of reorientation. And there is a translation of information between two different ways of seeing something. So I use that as a reference point, as well as I said, a specific behavior that is associated with a specific kind of cognitive processes. So it's not a matter of how it relates to space. So it's a kind of different question that I was bothered with, rather than what's the implication, no? So the implication, let's say, of these findings will not be will not be framed that way, but rather that the findings of this study is that where we have multi-directional views in areas where we can see different directions. Let's say controlling for landmarks and all like familiarity or smells or any other variable. They are more helpful in understanding where we are. Let's say it's a very simple thing. So for example, if you design an exit of a tube, don't do it, in a very small, narrow street. People would easily get lost there. Provide different views so one will be able to understand where they're heading, where they are, for like a more real.
I'm sure that people would very, automatically like talk about signage, right? So urban signage can really change the game with these things, right?
Yeah. But of course, you know what?
Yeah, what?
I was thinking that it's a very different thing of designing, having in mind that, okay, urban science can, and like urban science, I mean like the labels and the maps can save everything. But it's a very different, the sense of feeling that, okay, here I can easily get lost because I know that I will find myself. So this feeling of freedom, I don't know, to explore the city.
Yeah, but then exactly. So there's a lot of cities. I'm sure we all have these moments where you are in a city and then the scale of the city and how it's laid out. You kind of want to get lost in a fun way, like in a way that you feel, because in terms of navigation, there's a lot of things. A lot of parameters that come in, such as like safety, and then where do you feel more confident, and then I've seen one study which actually covers time. So how much people perceive time. So of course, if there's more events happening in a street, people perceive that they spent less time there. And then if there's nothing happening there, of course, you think you spent more time in that street. So there's a lot of like spontaneous moments in cities which can drag you towards other things, right?
And then also, I think in relation to time, it depends on if you want to go urgently somewhere, then time is like, and it was an experiment on that, the subjective perception of time and in relation to urgency of things.
Sure.
Which is very interesting,
Yeah, and then my kind of last question would be so usually we're walking, but then would that change if somebody was like on a bike, somebody was not walking, because now we're navigating things in VR, so it's mainly the visual perception that is directly there. But then I was wondering that, like, putting in other kind of personal transportation things, how would that change as well, the whole thing?
Yeah, of course they do change, and I think generally there is a tendency now for doing experiments. Of course, that requires a little funding to do that. But doing experiments where you wear the virtual reality headset, but you move around as well, which is, of course, it's more closely related to the experience that we have, and that's why it's more valid rather than sitting in front of the computer.
Yeah, so that's what like brain and body imaging is doing, exactly. So mapping both the body and the brain at the same time when we're moving in that environment.
Exactly, which is much more valid, much more difficult to do so.
Of course, that requires like a lab and so on. So yeah, I think we just crossed our limit. So if anybody else has any question, and if not, Efrosini, if you have any last things you want to say.
Just wanted to thank you a lot, everybody, for being here and your questions and your interest, and thank you, Firas, for inviting me. It was a pleasure doing this, having this talk with you, all of you.
Thank you very much. So yeah, everybody, that was what we have in hand tonight. We're gonna be having actually other people who are from around the UCL as well. working with navigation and spatial cognition later on. And then actually, we're gonna have guests talking about exactly what you were saying about